Hello everybody, this is Statistical Computing and Machine Learning. Nicholas Zabaros is speaking. So the lecture today, as well as the follow-up lecture, will be a review of Bayesian regression models, and we're going to try to focus our conversation more on the topic of variable selection, and in particularly mixing Gibbs sampling with these regression models. So let's see some of the topics we will cover today. We will literally go back to the beginning of the discussion we had on earlier lectures about regression models. I'm going to introduce again all the classical maximum likelihood estimators. I am going to give you different prior models that we have seen before, and then we will start talking on how to compute the posterior distributions, the marginal posterior distributions, the predictive distributions, the marginal likelihood, Bayes factors, confidence and credible intervals, and then eventually we will finish the discussion with variable selection. So in a high-dimensional regression problem, we will find means to select the variables that they are really needed to do the predictions of the output. So I will finish the discussion in the follow-up lecture with integrating Gibbs sampling for the task of Bayesian regression variable selection problem. All right, so some of the goals for today's lecture will be to review the Bayesian regression models. In many ways, you will benefit if you had followed the earlier lectures on this topic. If not, this lecture is going to be comprehensive, so I will try to cover all the details so nothing will be missed. And we will introduce various informative and uninformative priors. We will discuss again on how to compute confidence intervals, Bayes factors, posteriors, and predictive distributions, and marginal likelihoods. And eventually we will integrate Gibbs sampling with this task of variable selection for Bayesian regression models. Okay, so let's start this long lecture for today and discuss about linear regression models. So for those who have not seen this before, this is a supervised learning problem. We assume that we have some input x that I denote as bold x. So that's a vector, and I'm taking for simplicity that the output here is a scalar variable, y. So that takes, let's say, real values. And our training data set is this pair of xi, yi from I equal 1 to n, where n is the number of my training data. So the objective for the lecture today is literally to build a regression function that for each x allows us to predict y, and I call here the parameters of our regression model theta. So we will see how these parameters come and how we can do Bayesian analysis, how we can compute the posterior of these parameters. Now, the schematic that you see here, the image, obviously shows a caterpillar, and this particular example discusses about it's called the caterpillar example, and x are different environmental input variables such as the altitude, the slope, the height of trees and things like that, and y is the number of nests of these caterpillars. We're not really going to need the particulars of x and y's, but just, the particular data set is just not an arbitrary, but it's a data set that comes from this study of the number of nests of caterpillars. Okay, so our regression model is to build a function like this, and we're interested for linear regression problems. So y I mentioned is going to be a scalar response. The input variables, I denote them here as x1, x2, xk, so I have k of them. So this is important number to remember. The input variables in statistics are also called covariates. Also, you will see them under the name explanatory variables. For us, they are the input variables, okay? And again, I'm assuming here that they are continuous, real value inputs and outputs, but they can, in general regression problems. They can actually be discrete or they can be of mixed type. And I will show you an example on how to account for, for categorical variables in 1 second. So these are the input variables for our caterpillar regression problem. We have 10 of those. So it is an interesting, challenging problem. We have a 10-dimensionality input. That's not a very high dimensional input, but in the context of our course, being able to model something in 10 dimensions, that's certainly not a trivial task. Let me give you a schematic of the plots of the log of y. So y, remember, is the number of nests of this caterpillar. So log of y versus x1 to x9. And remember that our eventual task for today's and the follow-up lecture will be to compute if we really need these inputs x1 to x10 to predict the output y. And looking at this data, it is very hard to say, that I need x1, but maybe x5 is not needed. But certainly there may be relations between these variables that somehow will allow us, with a very small subset of them, to do as accurate predictions as if we include all input variables. So we will discuss this at the end of the lecture in 2 days from today. So how do we organize the information that is given to us in the training data set? So what we do is we put everything together in what is called a design matrix. And as in the earlier lectures, we denote this as capital X. If you remember, in earlier lectures, we will denote this as capital Phi. I do not have basis functions here, and that's why the notation capital X is more normal. Each row in the design matrix corresponds to one point in my training data set. And you remember I have k inputs, and you can guess that the first column, it corresponds to the bias term that I affiliate with a basis with an input dimension that always has the value 1. Okay, that's how this column comes about. So looking at this design matrix X, you can appreciate the fact that X is of dimensions n by k plus 1. That's something that you need to remember for the remaining of this lecture. So the design matrix is X times n plus 1. All right, so since we're going to use linear regression models, I will go directly to the form that our likelihood model is going to look like. It's going to be a Gaussian model. So effectively, X times beta will give me my mean response on my training data sets. Y will be the observed response, and there is a noise that sigma square that is Gaussian here. So the regression parameters beta and the noise level sigma square will be unknown, so something that we will need to compute from the given data. And if I can write this equation for the I training point, then the expectation of yi given my parameters and the design matrix X is given like this. There is no, of course, direct dependence on sigma square. That's why you don't see it here. And the variance is sigma square. Okay, so we're taking that the variance, we have an isotropic variance that does not depend on the input dimensions. All right, so I mentioned a while ago that I'm going to tell you at least in passing on how you can model other types of inputs, and particularly how to model what is called categorical inputs. So categorical inputs are inputs that are basically assigned to different groups or to different categories. That's from where the name, categorical distribution, if you like, comes from. Now, those categorical variables do take real value numbers, right? So they're not much different from these X values that you see here, but really what we're interested in is the category or the range that these variables are belonging to. So if you think of some categorical x that belongs in the interval a, b, I am more interested that they belong to that interval rather than the actual value within that interval. And actually, if you think when you have an interval, you can discretize it in a very fine way or in a very coarse way, so you can see that the actual value of a categorical variable doesn't make a lot of sense. So what we're interested is to what group or to what category does it belong. So if we have, let's say, m groups, 1 to m, that they're disjoint, okay, you can actually model within regression models these categorical variables using indicator functions, and I am adding those terms that you see in our previous regression function by having beta 1 times I1 of x, etc., beta m times Im of x. So I'm assuming that I have m different disjoint regions. So effectively x would belong to one of these groups or to one of these categories. So in some sense, I am going to have some constraint like the equation that you see in the bottom. And the way to enforce that constraint, you're going to have to fix one of these variables, these regression coefficients, to some fixed value, let's say 0, so they are not all independent. Or maybe you can enforce something like this through some prior model on the beta parameters. So in any way, these categorical variables are not difficult to include in the regression model, but today's lecture we will have finite value real regressors xi, and we will not bother with categorical variables. So let's go and start talking about classical estimators, and here literally I'm referring to maximum likelihood estimators. So again, this is our regression model, okay, nothing new yet, and I'm repeating the equations for the I training point. This is the expectation and this is the variance. You need to remember these expressions because they will come up all over the place. I'm going to make an assumption, right? You remember my design matrix X had n rows. Each of the rows corresponds to one training point, and each of the columns corresponds to each of my inputs. So I am going to assume that k plus 1 is less than n. All right, so I'm going to assume k plus 1 is less than n, and I'm going to assume that this design matrix X has a full rank. So the rank of X is k plus 1. So effectively, I'm going to assume that all the columns of the design matrix X are independent. So what this also implies, for those who remember things from linear algebra, is that the matrix X transpose X is invertible. So later on, when you see me writing X transpose X inverse, don't worry if that exists, because it does exist, because we're assuming that X has a full column rank. So the rank of X is k plus 1. Okay, so the likelihood for my particular model, which is now a function of beta and sigma square, is this Gaussian expanded here. So nothing yet fancy. All right, that's my Gaussian, and again, I look at this likelihood model as a function of the parameters beta and the parameter sigma square. Okay, obviously we will need to proceed now and maximize the likelihood or the log likelihood, or minimize maybe the minus the log likelihood with respect to beta and sigma square. We have done this type of calculations infinite times. They're straightforward. So when you take the minimization, say, of the negative log likelihood with respect to beta, you obtain the MLE estimate for beta that you see here, and that's our least squares estimate. The problem that you're solving is really a least squares problem. So when you take derivatives with respect to beta equal to 0, this is your MLE estimate. So when you see hat on the top of a symbol, implies the MLE estimate. Now, if you look in this estimator, beta hat is this matrix that is, we are assuming, known here. It's my training data. So it's a linear function of y, And remember, y from my likelihood model follows this Gaussian model. So now I can see that my MLE estimator follows also a Gaussian distribution, right? Where the mean of the new Gaussian distribution is going to be this matrix times x times b. This is what I have here. And then the variance is going to be this matrix times this variance times this matrix transpose. And that's what I have here. Okay? And when you simplify things like x transpose x and x transpose x inverse cancel out, so you do get that the MLE estimate for beta follows a Gaussian that has as a mean the true beta. So the estimator, immediately you can see it's an unbiased estimator, and then the variance comes to be sigma squared x transpose x inverse. So that's a nice and easy to obtain result. You can actually prove that the MLE estimate of beta is actually the best linear unbiased estimator of beta. So if you take any other unbiased linear estimator of beta, and let's say this is this weird symbol on the top of beta is any other unbiased linear estimator of beta, then you can show that for any vector A in Rk plus 1, the variance of A transpose beta hat, and again beta hat is my MLE estimate, is less or equal to the variance of A transpose this other unbiased linear estimator of beta. Okay, so now we need to take derivatives with respect to sigma squared and compute the MLE estimate for sigma squared, and this is what you obtain. And what we will need to do is we will need to do some calculations to figure out if this estimator is biased or unbiased. You already know the answer, but for those who have not seen these lectures before, we're going to try to prove, again from scratch, that this estimator is actually a biased estimator. Now we're going to, there are multiple ways, the long and the short way to do the derivation of this. So we're going to try to do a little bit slightly different proof of the biased nature of this estimator by introducing by introducing a matrix M, which is the projection of the data y, and remember the data vector y is a vector in Rn, so we're going to take the projection of y in the column space of the design matrix X. So this projection matrix is M equal X, X transpose X inverse, X transpose, okay? And it is an n by n matrix. So this matrix effectively y. When I operate M on y, effectively what I'm going to get is I'm going to get a combination of the columns of X. So I'm going to get X times beta, and actually that's how the MLE estimate comes, by projecting literally y on the column space of X. So let me use this definition, this projection matrix, and trying to use that information to compute the expectation of the MLE estimate of sigma squared. So if you take expectations of this, you're going to have the expectation of this, nice. Now I mentioned that M times Y is X times beta hat, right? That's really our least squares problem for computing the MLE estimate for beta. So I plug it in there, and now I can move y outside, and I can move the other y also to the right. So I have expectation of y transpose I minus m transpose I minus my. And I remind you, if you have a projection matrix like M, or even I minus m is also a projection matrix, you know that m squared is equal to m, and you know that I minus m squared is also equal to I minus m. So I can simplify this as I minus m. And now what I have is I have the expectation of y transpose I minus m times y over m. And to simplify this, I'm going to use the following theorem that I will prove in 1 or 2 slides from now, that if I have a n-dimensional random vector y with mean mu and covariance V, then the expectation of Y transpose AY for any constant matrix A is nothing else but the trace of A times this variance V plus mu transpose A mu. Okay, so let's make use of this. Let's accept it that this is a correct theorem. So I do have my problem in exactly the same setting as this theorem. So what I need is the expectation of Y, and I need also the expectation of Y transpose Y, and I know what those are, right? So what is the expectation of Y? Remember from your likelihood model, right? Y follows a Gaussian, and the mean of that Gaussian is x times beta. So I have plugged in here x times beta and beta transpose x transpose. And according to the theorem, the first term that I would need is the trace of A times V. So A is my matrix I minus M. And then I would need V, and V is the covariance of Y, all right? And remember again that Y follows a Gaussian with mean x times beta and a variance that is sigma square I. So that's what I have here, sigma square I. So I can pull sigma square outside. So I need to compute now the trace of In minus M, okay? And this term actually turns out to be 0. Look why. X times beta is the projection of beta in the column space of X. So X beta is already in the column space. So when I operate with M, I get X times beta because X times beta is already in the column space. So this product here of I minus M times X beta gives me X beta minus X beta, which is 0. So literally what I need to compute is the trace of In minus this projection matrix M. And here is one proof. The trace of In minus M is the trace of In, which is of course N, minus the trace of the projection matrix, which I write it like that. And I use a fundamental property of the trace. I can put the X transpose on the front, okay? So I get the trace of X transpose X times X transpose X minus 1. And this is an identity matrix of dimensions K1 by K1. So the trace of that is K plus 1. So the trace of In minus M is N minus K minus 1. Okay? So effectively this is the result that you see here. Okay? I'm also giving you another proof because this may be useful later in the slides. So what I'm actually stating here is that the trace of In minus M is also equal to the rank of In minus M. Okay, this is not in general true, but let me just state a few facts that may turn to be handy later in the lectures when we have to use again this matrix M. Remember this matrix M is N by N, right? And its rank is K plus 1, all right? And you may say, why is that? Well, let's look carefully. This matrix admits as eigenvectors these vectors x times beta. You can verify this immediately because if you multiply this projection matrix M with x beta, x transpose x is the identity, right? I'm sorry, x transpose x times x transpose x inverse gives you the identity. So you do get x times beta. So x times beta is an eigenvector of the projection matrix with eigenvalue 1. And how many combinations of the columns of x do we have of the form x times beta? Obviously we have k plus 1, right? Because you remember my design matrix has full column rank. So we have k plus 1 eigenvectors. So the rank of M is actually k plus 1. Now, if you take the orthogonal complement of M, that would be the matrix In minus M, you can actually prove that that matrix has a rank that is N minus K minus 1. That makes sense, right? Because if I add them, I need to have the two ranks to be equal to n. And you can show that in minus m has a rank n minus k minus 1 as follows. Take the vector z to be in the null space of x transpose. So by definition, take z so that x transpose z equal to 0. Now remember that x has dimensions n by k plus 1, so x transpose has dimensions k plus 1 by n, right? So we have k plus 1 independent rows, so this null space of x transpose has a rank that is n minus k minus 1, okay? And now why is that the rank of I minus m? Because observe that these are the eigenvectors of in minus m with eigenvalues 1. Because if I multiply this matrix by z, alright, so this is I minus m, if I multiply this by z, x transpose z is equal to 0, and then I have I times z, which is equal to z. So these are eigenvectors of I minus m. I have n minus k minus 1 independent z's, so the rank of in minus m is n minus k minus 1. I gave you lots of algebra that it's really in some way unrelated from our target problem, which is to compute if sigma square MLE is biased or not, but somehow those will be useful statements that we may need to use in the algebra, in the calculations later in this lecture today. So it's a good place to summarize for those who want to pay attention to the details. So coming back to this expectation of what I had here, this expectation, it turns out to be sigma square n minus k minus 1. So the expectation of the MLE estimate of sigma square is nothing else but 1 over n sigma square times n minus k minus 1. And that's bad news. It means that the MLE estimate of sigma square, it's actually a biased estimate, is not equal to the true sigma square. And now, if you have a lot of data, it's not a problem. If you have less data, you can define an unbiased version of sigma square, and that unbiased version is 1 over n minus k minus 1 times y minus x beta hat transpose y minus x beta hat. And I call, by the way, this quadratic error here s square. So s square, please remember that, is the error from y that I do when I approximate beta with my MLE estimate. So x beta hat is my regression function using this MLE estimate. So that's s square. So this unbiased estimate, I am claiming that is s square divided by n minus k minus 1. And you can actually see immediately that that's unbiased, because if you take the expectation of this, you will have 1 over n minus k minus 1 times the expectation of this quadratic here. And the expectation of that is n times the expectation of the MLE estimate of sigma square. And n times that is sigma square n minus k minus 1. So they cancel out and you get sigma square. So from now on, if you see a sigma hat square, remember that's the unbiased estimate of the MLE. That's why I put here the notation MLE explicitly, and I did not use bar yet, so that way I don't mix the notation. So when you see sigma hat square, that's the unbiased estimate of sigma square. All right, and I remind you again that the MLE estimate follows a Gaussian distribution with mean the true beta and a variance that the sigma square x transpose x inverse. So this is the variance of the MLE estimator. And again, you notice here, because I don't really know the true sigma square, I am writing this equation again using the unbiased estimator for sigma square. Okay? All right. Now, there was a little theorem that we use, and again, only for completeness of these notes, if anybody wants to show a proof, to prove this theorem, you can start from the expectation of y minus mu transpose A times y minus mu, and if you expand and you take the expectations, you can show that this is the expectation of y transpose A y minus mu transpose A mu. So already this minus that, that's nice. And then we have the expectation of this, and the expectation of that can be rewritten easily. You notice this thing inside the brackets is scalar, so I can write it, the scalar is the trace of a scalar. Then I can pull this y minus mu transpose to the right, like this. A is constant, I can pull it outside. And actually what I can do is I can reverse also the order of the trace and expectation. This is what I have done here, all right? So A is outside, and I have trace of A times this expectation, which is obviously the covariance matrix of Y. So I have trace of AV, and immediately you can see that the trace of AV plus mu transpose A mu is the expectation of Y transpose AY, and that's exactly what I used in proving that the MLE estimate of sigma squared was biased. This is what we did a few slides ago. Okay, now the MLE estimate follows this Gaussian distribution, and what is customary, if you take each of the components of the MLE estimate, it is customary to define what is called the T-statistic, which is the MLE estimate of the I component of beta minus beta I, that's the true beta, divided by the square root of sigma squared, that's the unbiased estimator again for sigma squared, times omega II, where omega II is the diagonal II element of X transpose X inverse. So this T-statistic follows a student T distribution with n minus k minus 1 degrees of freedom. That's the standard student T distribution. And of course, asymptotically, if you have lots of data, this converges to the normal distribution. Now, if you use this T-statistic, you can actually write down frequentist marginal confidence intervals. I have written those things down explicitly here, all right? So basically what this equation on the bottom says that the true beta I is the MLE minus this, and is bounded from above as the MLE estimate of beta I plus this, where of course you know what we have here is this f minus 1 evaluated at 1 minus alpha over 2. This is the 1 minus alpha over 2 quantile of the student T distribution. All right, so these are these confidence intervals from a frequentist point of view, and I remind you, for those who have not seen this before, there is nothing random about beta I, right? So this is the true estimate is a real number, it's not a random number. What is random is this confidence interval is random in the sense if you have another sampling, all right? So if you repeat this with some other data, effectively this beta I will vary. Sigma square, of course, because you estimate it from data, will vary. So the bounds in this confidence interval will actually vary. And so that's what introduces the randomness in beta I, okay? So what I want you to concentrate now is, let me say something else first, right? When you look at this equation on the top, the implication here is that the true beta, or the true beta I here, is in this interval with probability basically 100 of 1 times 1 minus alpha. So if you repeat this with different samples and with different MLE estimators, so 100 times 1 minus alpha % of the time, you will be within this interval that you see here. Okay, so So the probability is really 1 minus alpha, okay? And so let's use this equation now to start talking about some hypothesis testing, okay? Now, since our focus eventually is going to be variable selection, what we'll be interested is, I have a confidence interval for the variable beta I, and I'm wondering, do I need beta I times xi? So do I need the ith input variable? So in other ways, can I say something about the hypothesis H0 that beta I equal to 0? So it turns out that if this interval includes the 0, then somehow there is an evidence for the hypothesis beta I equal to 0 versus the alternative hypothesis H1 that beta I is not equal to 0, and this is at level alpha that defines effectively this confidence interval. Okay, so you can set this, so if the 0 is between this lower and upper bound, you can set this equal to 0, and then you can rewrite the equation on the top, and you can rewrite it in this form, where this absolute value of Ti, that by definition is given by this quantity that you see here, is less or equal than the 1 minus alpha over 2 quantile of the student T distribution. Okay? So effectively, what we have right now, we have a statement for comparing, for hypothesis testing, right? For testing the hypothesis H0 beta I equal to 0 versus the alternative hypothesis H1 where beta I is not equal to 0. And I'm going to give you this hypothesis testing written again with the same equation that I derived before. And the idea was, we said if this interval includes, the 0 point, right? The 0 point, so there is evidence then for the hypothesis that H0, that beta I is equal to 0. Now it turns out from a frequentist point of view that the statement that you see for this, for accepting the hypothesis H0, it actually has the same connotations as accepting or rejecting the hypothesis H0 using what's called the p-values, right? So let me remind you what these p-values are in a very sort of superficial way, because we don't want to get outside our Bayesian formalism in the lecture today. So the idea here is that there is a significant evidence against H0 if the p-value is smaller than alpha. So let me indicate what the p-value is. The p-value is the probability that my statistic will take higher values than the ones that I observed, which is this little Ti given here in absolute value. So if you think Ti with a plus and a minus sign defining this central interval and the two tails of the student T distribution, basically the corresponding probabilities of the tails, which is this term plus this term, have to be less than alpha. So effectively, this criterion based on the p-value tells you that there is a significant evidence against H0 if this p-value is less than alpha. So effectively, the probability that we will observe values of the statistic that they are higher than this value of absolute value of little Ti should be less than alpha implies nothing else but that this absolute value of Ti being greater or equal than this 1 minus alpha over 2 quantile of the student T distribution that we had seen on the slide before. So effectively on the slide before, this criterion was written with less or equal in our inequality, but the previous criteria was for accepting the hypothesis H0. Here is evidence against H0, so the two things are actually one and the same thing. Okay, so to avoid sort of further confusion with this frequentist point of view, keep in mind that these p-values are the same as the standard hypothesis testing, and in some way checking if this confidence interval includes the zero value, also that is evidence for the hypothesis H0. So all of these things turn out to be equivalent. So let me, for the particular data of the caterpillar problem, so let me do some calculations. I am going to calculate for each of my input variables, including my bias term, the MLE estimate of the parameters beta. This is the standard error for each of these variables, all right? This is the little ti that I had before, and these are the p-values. And if I take the alpha level to be 0.05, you can see that there is sufficient evidence against the hypothesis H0 for the bias term, for beta 1, for beta 2, for beta 4 and beta 5, because these p-values are less than alpha, less than 0.05. Okay, which means if you're going to do variable selection, right, you will need to keep these variables. The remaining of these variables can be omitted because there is not significant evidence for them based on this frequentist way of looking at things, which is either using the p-values or the hypothesis testing that I discussed the last few minutes. Okay, so actually we have already seen one way, the frequentist way of doing variable selection, that is uses these intervals that we have seen, and if those intervals contain the value 0, then there is evidence for the hypothesis H0, and again we extended this to the p-values, getting the same equivalent results. Okay, so let's go to our likelihood model. So the likelihood model is the equation I had written before. I am going to rewrite this equation in a standard fashion that is a very important formula to remember, because sort of it will be a starting point for many Gaussian likelihoods. So as you can see here, what I have done on my exponential here, I added and subtracted the MLE estimate beta hat. So if you perform the multiplications, you can actually simplify things eventually, and the likelihood can be written, the exponential can involve only s squared, and I remind you what s squared is, right? S squared was the error that I do from my training data y when I use beta hat in my regression function, where beta hat is the MLE estimate. And then here this quadratic term involves the difference between beta and n beta hat, okay? So where again beta hat is my MLE estimate, and I notice here this parenthesis should be a smaller parenthesis, right? So we will correct this in the post-it slides. Okay, so I think we're ready to start talking about Bayesian analysis, and talking about Bayesian analysis means we need to start introducing priors. So we will talk about this first level prior analysis, and obviously we will start with conjugate priors, and then once we have these prior models, we will produce the posterior distributions of the parameters, marginal posteriors, then we will produce the predictive distribution, we will produce the marginal likelihood, and then the Bayes factors. And we will repeat this type of calculations to some extent for various priors that we will need to use in today's lecture and the follow-up lecture. So we start with conjugate priors, and I know we already have discussed this in an earlier lecture, so for some may be a repeat, for others may be new material. So the priors that we're going to use, and I don't have time to extrapolate looking at the likelihood model, but somehow The prior that you see here is going to be conjugate in the sense that if you multiply with the likelihood, the posterior is going to be of the same form but with different parameters. And what is this form of the prior? Given sigma squared, the regression parameters follow a Gaussian that is defined with some prior mean that is tilde of b, and then you notice for the variance I have sigma squared m minus 1, sigma squared m minus 1. Remember, beta is a vector of dimensions k plus 1, so m is k plus 1 by k plus 1, is symmetric, is positive definite, and sigma squared then is an inverse gamma distribution with parameters a and b. Okay, so you're going to see lots of algebra and try to concentrate on the big picture rather than on the on these complex, otherwise complex equations. But you need to be able to do this type of calculations because you may have to repeat them for maybe some other prior model that it's of value to your research. So if you expand this Gaussian and this inverse gamma distribution, you multiply with your likelihood model. This is your likelihood model. This is the Gaussian from your prior, right? And this is the inverse gamma distribution. And you do all the multiplications, you do get something that looks the way that you see it on the bottom of this line. Okay? So now we will need to produce the posterior distribution for some closed form posterior distribution for the join of beta and sigma square, and you anticipate that that distribution is going to be a Gaussian inverse gamma distribution. So the first thing we're going to do is we're going to take sigma square constant and look at all the terms that involve beta and try to identify how this Gaussian is going to come up. Okay, so if you actually do this and you keep sigma square constant and you try to close the square on beta, you're going to get a quadratic term that seems to be corresponding to a Gaussian with this as a mean, all right? And I am not accounting here for the terms of sigma square, but you can immediately see this is going to be the inverse of the covariance matrix. So immediately I see a Gaussian there, and here is this Gaussian. So beta given sigma square and given my training data is going to be a Gaussian with a mean that you see here, all right? And the covariance matrix sigma square m plus x transpose x inverse. So the Bayes estimate for beta given sigma square is this matrix, which is nice. You can see it's a weighted average of the prior of beta and of the MLE estimate of beta. And the variance, right, is sigma square m plus x transpose x inverse. Okay, so that's the distribution of beta given sigma squared. Now we have to produce the posterior of sigma squared that has to come to be an inverse gamma distribution. So what you will need to produce the distribution of sigma squared, you will need to integrate from this joint posterior that I had before, you will need to integrate beta out. And you remember beta was coming with this exponential that is the Gaussian that you saw before. So if you integrate this exponential out, you will get the marginalization factor for a Gaussian. And what is left is actually an inverse gamma distribution hidden in all of these complex terms. Okay? And you can, I can go and state what the result will be, but let me just take you a few more steps to see some of the algebra that is involved to simplify the calculations. So I'm going to use two identities for matrices. One I call an identity A, the other one I call it an identity B, okay? And again, what you see here for the marginal posterior of sigma square, okay? It comes nothing else by integrating beta out using the normalization of beta, and whatever is left in terms of sigma square, that's the form of the marginal posterior of sigma square. And you notice I don't use y as a conditioning on the data because the MLE estimate of beta contains all the information that appears to be needed for this posterior of sigma square. So I'm going to use this identities A and B that you saw before. So what I'm going to need is, I'm going to need to expand this, all right? So I am expanding it, okay? And for this term, I'm going to use identity A, okay? For this term, I am going to use identity B that I had before. This you can actually show with trivial algebra, that is equal to m minus x transpose x, m plus x transpose x inverse times m. You can actually show this immediately. If you take this minus term on the other side, you're going to get an m plus x transpose x, which together with m x transpose x inverse will cancel out, so you'll be left with m. So this is m equal to m. And then what I'm going to do is I'm going to use the identity B for this, okay? And if you put all of this together, all right, and you complete the algebra, effectively this is what you get. You get a very nice form for the marginal posterior of sigma square, looking like this. I remind you again, this tilde of B is the prior mean of beta. This is the MLE estimate of beta. S squared, if you remember, is the error using beta hat in my regression function. That's the error y minus x beta hat squared, basically. This parameter beta comes from my prior, my inverse gamma prior, together with the parameter alpha, and n is my the number of my training data points. So if you look at formulas for inverse gamma distributions, this is an inverse gamma distribution with parameter n over 2 plus alpha, and then a parameter, the second parameter is all these terms that you see here that look long terms, but they're actually very nice, very compact form. So the marginal then posterior is an inverse gamma distribution, and if it's an inverse gamma distribution, you can do anything you want with it. If somebody asks you what is the Bayes estimate, what's the mean estimate for sigma square, you can look at the formulas and say, you know, the mean of an inverse gamma distribution is beta over alpha minus 1. So if you take this as your beta divided by this minus 1, you actually get a nice Bayes estimate for the posterior mean of sigma squared. So this actually will come to be handy. And there is one little calculation, but maybe with a little bit more algebra that we need to complete as well. Somebody will ask is, and what is the marginal posterior of beta? Because if you remember, we derive the posterior of beta given sigma squared. So what is the marginal posterior of beta? And of course, immediately you can say, no big deal. I'm going to take that the distribution of beta given sigma squared, which is Gaussian. I'm going to multiply it with this inverse gamma distribution, and then do nothing else but integrate sigma squared out. And the rest is algebra, literally, okay? And before I show you this algebra, actually, let me mention that the formulas that we derive up now, you can actually use, if you like, simplistic assumptions on the form of the prior model that we had, and you can come up with simplifications that lead, for example, to what's called ridge regression, which is nothing else but regularized least squares. And I wanted to show you actually before I proceed to the marginal posterior beta. So let's take this matrix M to be the identity matrix divided by some scale parameter C, and I'm going to take the mean of my prior to be equal to 0. So if you look at the general formulas that we had for the Bayes estimate for beta given sigma square, that's the equation that we had. So if you plug in m to be given by this, and if you plug in tilde of b to be equal to 0, what you obtain is the following. You obtain m, which is I divided by c, plus x transpose x inverse. This is 0, and then you get x transpose x beta hat. And you remember from the definition of beta hat, x transpose x beta hat is really x transpose y. And this Bayes estimate that you see here under these simplifications in my prior model is really regularized least squares, where the regularization parameter is 1 over c. And this model, this regularized least squares model, is known as Ridge estimator. So if you hear the name Ridge estimator, basically is derived from the previous model by using this simplified m and using as a prior mean 0. All right, so let's go to the problem that I mentioned before, which is integrating sigma square out so we can produce a marginal posterior for beta. So really what I need to do is I need to take this distribution, which is a Gaussian. We derive it, okay? We need to multiply this with my marginal posterior for sigma square, which is an inverse gamma, and we need to do the integration in sigma square. I am not going to bug you with all the details. They're given in the slides, and I encourage you to look at them so that you become familiar on how to do these calculations, thinking that it's not something magic. It's simple, basically calculus, okay? So what I'm going to do is I use two change of variables to do the integration. I could have done this directly in one step, but this is how it is. So I use tau 1 over sigma squared. So basically tau is the precision to start with. So I went from integration sigma squared to integration in tau. And then I introduce another variable. So when you look in, when you expand this Gaussian, right, you will get an exponential term. And then when you expand the inverse gamma distribution, you will also get an exponential term. So when you look at minus that exponential term, what you have is 1 over 2 sigma squared, all right, which is tau over 2, times all this bracket that I call g, and I introduce a new variable that I call z. So z is tau times 1/2 times this g, where g is the whole bracket that I get in the exponential when I expand my Gaussian and my inverse gamma distribution. So the integration from sigma squared became an integration in tau, and the integration in tau becomes now an integration in z, where I treat this whole term in the bracket g to be constant because it does not involve sigma on it, it's constant. So if you do the integration in z, what actually you get that this marginal distribution in beta is really nothing else but z to this power that turns out to be minus k over 2 minus n over 2 minus a minus 1/2. And for me to do this type of calculations, I use a symbolic online integrator. So you don't really have to know anything. You plug in this exponential in your symbolic integrator, and basically gives you, it spells out for you that this is what you get at the end of the day. Okay, so the term with z was pulled outside, and then you had an integral that turns out to be a constant. So effectively, this is what I get. Okay, so and remember we had defined z to be that big term in the exponential. So at the end of the day, this leads to distribution that is of this form. And for those familiar with the student t distribution, this spells out basically that this is a student t distribution. The only task that you have is to put it appropriately in the form of a student t distribution that looks like what you see on the bottom of this slide. Okay, and I can tell you that if you do the calculations properly, you can identify what the degrees of freedom new for the student t distribution are. You know the dimensionality p here is k plus 1, and of course you're going to have to define what sigma is, and I am going to give you all of these results, and here they are. So the marginal distribution of beta is a student t distribution with k plus 1 degrees of freedom. With k plus 1 in k plus 1 dimensions, with n plus 2a degrees of freedom with mean mu, and the variance, the covariance matrix is sigma hat, that is given by this It looks a very complicated form, but a very elegant form, right? Because it's compact. It involves the information from the prior and the data through the MLE. And that's the end of the story. So we basically have the marginal distribution for beta being a student T distribution. And again, here is a summary of the student T distribution. And if somebody asks you what is the Bayes estimate for the marginal of B, you look at the student T distribution, you know what the mean is equal to mu, so the Bayes estimate is literally what you see here. And again, you can see this is a weighted average between the prior mean, that is this bit tilde, and the MLE estimate, which is this beta hat. Okay? All right. Now, can we now compute a predictive distribution for our problem? In other ways, if we have a new input that I here define as this design variable tilde of x, all right, so this is a test design matrix, if you like, can I actually produce what the distribution for my output tilde of y will be. And this is the posterior predictive distribution because I'm writing it given x and given y. Now what I'm going to do is, just to make the calculation easy for me, I am going to produce the predicted distribution first given sigma square, and eventually I'm going to integrate sigma square out. Okay, so first I'm going to do the calculation given sigma square, just to make the calculation easy. Okay, so look how easy the calculation may be. If in addition to sigma square I knew what beta is, then I know that this distribution, this predictive distribution given beta and sigma square, is my likelihood model with a mean tilde of x times beta, and my covariance matrix to be sigma square IM. I have here M test inputs. That's where this IM comes. Okay. Now, the question is now, do I know what the posterior distribution of beta is given sigma square? And the answer is yes. That's a Gaussian. All right. So that's what we derived before, that the posterior distribution of beta given sigma square is a Gaussian. So effectively, this predictive distribution of tilde of y given sigma square is nothing else but the integral of this predictive distribution given beta times the posterior of beta. Okay, so effectively the predictive distribution given sigma square is the integral of my likelihood given beta and sigma square, and then times the posterior with the beta integrated out. And as I mentioned, we're going to integrate eventually sigma square out later on, but right now I have this condition sigma square, and I am integrating, as you see on this formula, beta out. Now, I mentioned that this is a Gaussian, right? You can see it here. This posterior, this condition posterior is a Gaussian, and when you integrate beta out, obviously you're going to get a Gaussian. So if this then turns out to be a Gaussian, rather than doing this integral and spending 2 or 3 pages of calculation, can you actually simply compute the mean and the variance of that Gaussian and then write it down explicitly from there? And the answer is yes, we can do this without performing this long integration. And the way we can do this is by using the formulas of what is called iterative expectation formula. So let me introduce those formulas, and I'm going to describe them with words. Okay. So what I have here is I have the expectation of x given z, and what I have done is I have written this expectation as the expectation of the expectation where inside I'm conditioning on y. So here I'm computing the expectation of x conditioning on y, and then the expectation on the outside will be averaging over y. So if I can compute some conditional expectation easily, then I can average with respect to the variable y, and I can come back to my original expectation of x given z. And similarly for the variance, this variance of x given z can be written as the variance of the conditional expectation of x given y plus the expectation of the variance of x given y. So again, this is the expectation with respect to y of the conditional variance of x given y given z. Now, there is a proof of this in this slide, which is you can find in any statistics book or on Wikipedia. But let me just tell you what the idea is, right? You remember that I had this conditional distribution, predictive distribution of beta and sigma squared being this Gaussian, and I had this posterior being this Gaussian. So you know what I need to do is I need to compute the distribution of y tilde given sigma squared and all my data. Okay, so to compute the mean of this distribution, what I can do is I can condition the tilde of y on beta and then take the expectation with respect to beta. But the tilde of y given beta and sigma squared is the expectation of that is nothing else but x tilde times beta, which is what I have here. And then if I need the expectation with respect to beta, the expectation with respect to beta is nothing else but this long term that you see there, and that's what I have here. And similarly for the variance, I can write this variance of tilde of y given sigma squared and all my data to be the expectation with respect to beta of the variance of tilde of y given beta given sigma squared, which is actually sigma square I, which is constant. I don't have to do much with it. And then I have the variance with respect to beta of the expectation of tilde y. The expectation is x tilde times beta. And then I need the variance of this. And the variance of this would be nothing else but x tilde transpose times the variance of beta. And the variance of beta is nothing else but sigma square m plus x transpose x inverse. And when you combine the two terms, you have everything you need. So effectively, the predictive distribution given sigma squared, that's very important, is a Gaussian, m-dimensional Gaussian with this mean and this variance, all right? So that's wonderful, okay? And now what you need is you need to integrate sigma squared. And to integrate sigma squared, we know that the marginal posterior of sigma squared is an inverse gamma. So we're going to have to multiply a Gaussian with an inverse gamma and integrate sigma squared out. I don't really have to tell you that's a repeat of the calculation I did before. You know the answer is going to turn out to be a student T distribution. So if you take this Gaussian, you multiply with the inverse gamma, you're going to have to change the integration, expand these terms, expand this, take everything on the exponential, take everything inside the exponential that doesn't depend on sigma square, call it some constant number, and somehow do the integration. And if you do all of this, okay, I am going to give you the final answer. The final answer, following exactly the same procedure as before, turns out to be a student T distribution, if I can find it. And it is a student T distribution in m dimensions with n plus 2a degrees of freedom with this mean, all right, with this mean and this covariance matrix. So we're done. We have a student T distribution for the predictive distribution. Okay, so we have again a student T distribution for the predictive distribution. That's a major accomplishment, right? We have managed to actually get in a closed form this predictive distribution. All right, so let's see how you're going to implement this in practice and what type of parameters you may use. So it is not uncommon to use as a prior mean to be the zero vector. This is what I have here. And we're going to use for m exactly as we had before, the identity matrix divided by this scale parameter c. So effectively my prior model looks like that in this particular case, okay? So in the results that you're going to see, the parameters in the prior for sigma squared in the inverse gamma distribution were selected to be A equal to 2.1 and B equal to 2, okay? And the intuition, by the way, when you look at this prior model, the intuition for C is that the higher the value of C is, the more diffuse the prior on beta is. So somebody in practice will anticipate that the higher the C value, the less the effect of the C is going to be, because the anticipation is that maybe this will become an uninformed prior. But as we will see, rather disappointingly, I may say, that will not be the case, and there is an effect of C that is going to be there in our calculation. So somehow we're going to have to do something by modifying this model. Okay, so we will see this in a little while. So let me actually show you this effect of C. So what we're doing is we're estimating the Bayes estimate for sigma squared, that's the posterior mean, and I'm only taking the bias parameter beta 0, so that's the Bayes estimate for beta 0, and also that's the marginal variance for beta 0, and I use different values of C starting from very small to very big. You notice as C increases, these values seem to be stabilized, but there is a huge effect of the values of C. So going from 10, let's say, to 100, you can see that the effects on the mean and the variance of beta 0 and sigma square is significant, which means that this choice of parameters that you saw in the slide before, obviously they don't lead to an uniform prior. Contrary, this prior is very informed because the effect of C is significant. Okay, so the formulas again that I use are the ones that we just derived. So literally what you need to is to just plug in your particular choices for the prior, and that will give you directly the Bayes estimates for sigma squared and beta 0, as well as the variance for beta 0. Okay, so what you see here are the rest of the parameters beta I. So I am tabulating the Bayes estimate for beta I as well as the variance, and I'm fixing the value of the parameters C to be 100. And again, if I change C, the effect on these variables will be significant. Okay, so somehow, even though these estimates seem to stabilize for a high value of the parameter C, there is, there is an effect that stays, especially on the noise variable sigma square and on the beta 0 parameter, that somehow point that this prior is not an informative at all. Okay, so it's not an informative at all. Now, I'm not showing you the effects of the parameters A and B from the inverse gamma prior on sigma squared, but also I can tell you that those parameters A and B also have a long-lasting effect on my Bayes estimates, and in some sense we're going to need to fix that as well. That inverse gamma seems to be anything but uninformative, so we will need to fix that. Okay, so this is what this slide basically summarizes, that somehow this particular prior that we use, it is not uninformative at all, even on the limit of very large C, so we're going to have to do something to fix these problems. So how do we fix? We fix these problems by modifying the previous prior analysis and going from the fully conjugate prior modeling that we had before, the generic conjugate model, to go now to what's called the Zellner G-Prior. So what is the Zellner G-Prior? Has the same structure as before. You can still see my prior on beta given sigma squared is a Gaussian. Sigma squared now I'm taking it to be an improper Jeffreys prior, 1 over sigma squared. And what is important to note is that that matrix M that I had before now becomes X transpose X. Okay, so somehow the correlation structure in my prior to define this variance matrix is fixed, okay, and the structure there involves a matrix X transpose X inverse, okay. This in some way will simplify the algebra, but you will see it will fix some but not all of the problems that we had with a fully conjugate prior analysis that we discussed up to now. So what I have to do, unfortunately, I'm going to have to repeat all the calculations we have done up to now for this prior. So we're going to have to produce the posterior for beta and sigma square. We're going to have to produce the marginal posteriors. We're going to have to produce the predictive distribution. And then we may talk about Bayes factors, confidence intervals, and the like. So lots of the calculations will look very similar to what we have done before. So I'm going to try to a little bit advance my calculations so I don't repeat the algebra, and you guys can consult the notes where all the details are given for you ready to review. Okay, so let me just, so I'm going to discuss later on what the particular meaning of C is. So I am going to wait until we get some Bayes estimates for the parameters beta, and then I will come back to this at a later point. So what we have to do is we have to take my likelihood model, which is the same Gaussian model that you see here, right? This exponential times the normalizing factor, multiply with the prior beta given sigma square, which is, I'm sorry, this whole thing, parenthesis, is my likelihood model. You remember I had written this as S squared plus this error term, right? So this whole big parenthesis is my likelihood model. And this term plus this term is my prior beta given sigma square. And that's my Jeffreys prior, which is 1 over sigma squared. So what you really have to do is, right, first, produce a posterior of beta given sigma square. So take sigma square, fix it, and try to close the square on beta, and that better come to be a Gaussian. So let me show you how that is going to look like. If you close the square, if you fix sigma square, close the square on beta, you can immediately recognize a Gaussian there, and that Gaussian is given on the bottom of this slide, okay? Now, once you have that Gaussian, you can eliminate beta. You can eliminate beta by combining. Once you close the square here, right, in the fashion that you see here, right? So obviously you had to add some terms and subtract some terms to close the square. But once you close the square, you can integrate beta out, and you're going to be left only with the normalizing factor of that Gaussian. And the remaining terms will only be terms that depend on sigma square, and that will give you hopefully an inverse gamma distribution. So this is where the closing of the square term comes. So this, if you integrate it out, you will only get a normalization factor and for a Gaussian. And what is left is basically an inverse gamma distribution, and that's the final answer. Okay, so this is the marginal of sigma square is this very nice inverse gamma distribution. Now, if you have the posterior marginal of sigma square, then you can actually compute the marginal posterior of beta by multiplying that beta given sigma square distribution that I had before, that Gaussian, with this particular inverse gamma, and then integrating sigma square out. And I don't need to tell you, the answer is going to come to be a student T distribution. So when you do all of this, this is what you get. This is the this is the marginal of beta. That's the posterior of beta. Immediately, you can recognize this as your Bayes estimate for beta, and you can use the formulas for the student T distribution. So if you need the variance of beta, this is going to be n divided by n minus 2 times all of these long metrics. So anything you need to do about this student T-distribution, you can derive it from the formulas that you see on the bottom of the slide. So let's concentrate for 1 second on the mean of this, all right? So the mean is C divided by C plus 1 times this parenthesis. So if I can put things together, you can see tilde beta is the prior, and C times beta hat, and remember beta hat is the MLE estimate. So if sigma is equal to 100, right, you can see that the prior weighs 1% of the sample, right? That's the information contained on this MLE estimate of beta. Okay, so so that's the way to interpret actually this scale parameter C that it was also given in an earlier slide that I passed by. So if you look at the variance now of beta, this is the formula. Again, it's a very nice closed formula, closed form formula that gives you the variance of this marginal of beta. All right. Now, if C equal to 1, right, then you can actually see that the Bayes estimate for beta is actually the average of the MLE estimate of beta and the prior mean. All right. So that's also an interesting result. And from the sigma square posterior, the marginal posterior of sigma square, you can also derive the Bayes estimate for sigma square. So you can use the mean of the inverse gamma distribution, that is the beta parameter divided by the alpha parameter minus 1. So it's all of this minus this minus 1, and that's the Bayes estimate for sigma squared. Okay, and here are some results, right? So what I have is I'm selecting the parameter C to be 100. I am showing you all the beta i's, right, corresponding to all the input directions, starting with the bias term. This is the Bayes estimate, that the expectation of beta I. That's the variance of beta I. And I'm also giving you values of the Bayes factor, the log of the Bayes factor for each of the variables. So this is B10I, okay? So the formulas that I'm using for the expectation again of beta I and the variance of beta I are the formulas that we have seen in our earlier derivations. Now, the actual derivation for the Bayes factor will have to wait because if you remember, the Bayes factor will require that we calculate the marginal likelihood. So we're going to have to discuss on how to do that. You remember the Bayes factor compares two models, and here is model 1 versus model 0. So model 0 is the model, there is a superscript I here that corresponds to each of these variables, right? So the model 0 is the model where I have removed the ith variable from the model. So for example, if you look at the first term, beta 1x1, so I have removed that completely, and that would correspond to this Bayes factor B101, okay? Maybe we can use I for the intercept or for the bias term. So you can actually, looking at these numbers, if you remember the meaning of the Bayes factors, right? So this is the Bayes factor of model 1, where the parameter is kept, the parameter I is kept, versus model 0, where the parameter I is removed. You can see the numbers that they are marked here with stars. There is evidence against the hypothesis H0 that the parameter is equal to 0, because this Bayes factor seemed to be significant, okay? And again, significant is relative here, so these 4 stars means the evidence against the 0 is decisive, 3 stars strong, 1 star poor, but somehow here is one more different way now, maybe the first way in a Bayesian setting that we see how to do variable selection using Bayes factors. All right, and the only thing that you will need is you will need to be able to compute these Bayes factors by computing first the marginal likelihoods for the model 1 where all the variables are being kept, and the model 0 where you know one of the variables is out of the model, in particularly variable I, okay, from I equals 0 to 10. All right, so now this particular calculations are done for C equal to 100. If you actually repeat this for C 1000, the answers actually, if I can go back and forth, they vary to some degree. So if I look, let's say, at the intercept here, is 10.8895, okay? So here is 10.9874. So the effects, for example, on the Bayes estimate for beta 0 is not as significant as what we had with the full conjugate prior analysis before. So using the Zellner G-Prior has a little bit helped in resolving this problem, the dependency on C, but not completely, okay, not completely. We're going to come back to discuss on how to eliminate completely the effect of this parameter C in our predictions, and we will do that shortly. All right, so next what I want to show you is how for this Zellner G-Prior we are going to compute predictions. And again, the algebra is very similar to what we discussed before, right? So if I can put all the equations down, first we're going to produce the predictions for a given sigma square, right? The predictions for a given sigma square. Then we're going to integrate sigma square by multiplying and integrating out sigma square, and this posterior distribution of sigma square is inverse gamma. This distribution, you can guess, is going to come to be a Gaussian, and the way we're going to calculate that Gaussian is by using this iterative expectation formulas that we saw before. So we're going to start by calculating the expectation and the variance of this tilde of y given beta and sigma square, and then we're going to put on the top of that those identities that you saw before where we're going to average over beta, right, using the posterior of beta. So given sigma square, the posterior of beta is this Gaussian that we saw before, all right, and so that's convenient, okay. And here is the iterative expectation formula. It says if you want the expectation of tilde of y given sigma square, compute the expectation if you also knew beta, and if you also knew beta, then my likelihood model for y hat for this tilde of y will be x tilde times beta, all right? And then I'm going to need the expectation of beta given sigma square, which is given by this formula. So here is the expectation, okay? So the expectation of the predictive distribution of tilde of y given sigma square is really my design matrix tilde of x times this nice thing here, which actually is nothing else but the Bayes estimate for beta given sigma square, all right? So, and actually it turns out that somehow this formula is independent of sigma square, okay? Because you don't see any sigma square anywhere here. So it turns out that it's independent of sigma square, and again, you have an intuitive result that says that this is the product of the design matrix tilde of x times the Bayes estimate for beta that you see on the slide on the top. Now, the variance, similar things, right? So this variance of tilde of y given sigma square, first you're going to have to take the expectation with respect to beta of the variance given beta and sigma square, and the variance of given beta and sigma square, you know, it's sigma square IM, right? That's from my likelihood model. And then you're going to have the variance with respect to beta of the expectation of tilde of y given beta and sigma square, which is this formula. The expectation of tilde of y is x times beta, all right? X times beta. And then you're going to need to have the variance of this term with respect to beta, and that's that variance. And so this is the answer, right? So the first term gives you sigma square IM, and the second gives you tilde of x transpose times the variance of beta, which is given by this formula. And you remember my model is a Gaussian, right? So this is a Gaussian, this is an inverse gamma. When you integrate sigma square, you do exactly the algebra that I mentioned before, and you know what distribution you're going to get. You're going to get a student T distribution that defines the predictive distribution of y for inputs tilde of x, given your data y and x and capital X. All right. So I'm not going to do this full calculations, and really what I want to do is I want to go back to the marginal posterior for beta that you remember was, if you look back a few slides, for the Zellner G-Prior was a student T distribution in k plus 1 dimensions with n degrees of freedom with this mean and this variance, right? So what I'm going to do is I'm going to concentrate on each of the variables beta I alone, so I can write down some highest posterior density region, some credible regions for this posterior, right? So let me write down this equation for the variable beta I, okay? And omega I here is nothing else but the II element of this covariance matrix. So in this case, actually, omega II is the II element of x transpose x inverse. Okay. So what I'm going to do is I'm going to introduce some intermediate variables. I'm going to define all of these components to be a tau vector. All right. So that's one thing, and I am going to define. You remember here I had this whole matrix. So this is my ij element of kij is going to be the ij element of this matrix. Okay, and I'm going to define a normalized variable zeta I that is nothing else but beta I minus tau I, right, minus the mean, defined by the standard error, which is going to be the square root of kii. And I'm going to do all of this because then I can write the 1 minus alpha highest posterior density region, and this is the formula for that region. Okay? So we have now a confidence region, and this is a Bayesian credible region. So this is a highest posterior density region, is very much different from what we have seen before with the frequentist point of view. And of course one can ask, can I look if the zero value is within this interval? And if that's the case, can then say that there is significant evidence for the hypothesis H0 beta I equal to 0? The answer is, unfortunately, you cannot do this in the context of Bayesian analysis the way frequentist statisticians are doing. Now, you may see textbooks and papers where actually they point that there is evidence using these HPD regions that if the zero is contained on this interval, then there is significant evidence for the hypothesis H0 beta I equal to 0. But generally speaking, you cannot use these arguments the same way you do in a frequentist statistics setting. All right. So you remember we discussed about the Bayes factor a while ago. So if we discuss about the Bayes factor, I need to at least tell you how this Bayes factor is computed. And to compute the Bayes factor, you need to have the normalization factor, right? So you need to have the normalization factor. And so I'm going to have to do this calculation. Let me see what we have here, right? So the this is my prior model. Remember, this is the Zellner G-Prior. Beta given sigma square follows this. So x times beta follows a Gaussian with a mean x tilde of beta. And this covariance matrix now becomes, if I multiply by x, I'm going to have x transpose. So it becomes something like that, all right? And if I add my noise sigma square that I have in my likelihood, so basically I can write down that the distribution of y given sigma square is a Gaussian that you see here with this particular mean and this particular variance. Remember, to calculate the marginal distribution of the of y, what you need to do is you need to take your likelihood, multiply with the priors of all your parameters and integrate them out. So what really I have done here is I have written my likelihood where beta has already been has been already integrated out, okay? And the only thing that I have here is I have sigma square, all right? So effectively now what I can do is I can multiply this marginal likelihood, if I can call it, right, where beta is integrated out, multiply this with the Jeffreys prior for sigma square, which is 1 over sigma square, and then integrate sigma square out. And if you do all of this, then you actually will get the marginal likelihood of y, where both beta and sigma square have been integrated out. The algebra is not actually very painful. It's not very much different from what we have seen before, but there are two tricky parts in the calculation that I need to be able to tell you a word, so you can actually, when you look at the slides, things make a little bit of sense. So remember, to get the marginal likelihood, and I'm keeping C to be some constant parameter right now, I have to multiply this likelihood where beta has been integrated out, and you notice this likelihood, this is what I get in the exponent. I'm going to have the inverse of this matrix, all right, coming from this Gaussian. And then I am going to have the determinant of this matrix to a power minus 1/2, or because I have it on the denominator, to a power 1/2. And so what I'm going to need to show you is that the determinant of this matrix is really C plus 1 times K plus 1, okay? So we're going to have to show that the determinant of this matrix is C plus 1 raised to the power K plus 1. And then we are going to have to do some algebra to simplify this exponential term so we can do this integration analytically. So let's concentrate on the two things separately. First, do some simplifications on this exponential, and then show that the determinant of this matrix is C plus 1 to a power K plus 1. So if you if you keep things in, if you do things properly, right, eventually what you get is you get a formula that looks what you see at the end of this slide, right? So you notice here this exponential has disappeared, and I see much simpler terms. So I'm going to tell you how you are getting this, but at least the normalization from the determinant comes exactly as it was in the original term. So I'm going to tell you how this term is being computed, and the rest is an integral in sigma squared that you can perform easily. You can take everything that you have here, call it some constant value, and then you will have to perform an integration of sigma square, which will not be very easy, very difficult to do. It's similar to what we did before to derive student t distributions. So first, the simplification of that term. you will need to use this matrix identity that you see here, okay? And I am not going to prove it. The proof is in the slides. So if you use this identity, that the inverse of this is given like that, then you can simplify that exponential term to what I showed you on the bottom of the previous slide. Simply take this, plug it in, expand all the terms, this is what you get. And the last thing I'm going to show you is that the determinant of this matrix is c plus 1 to the power k plus 1, okay? And the question is why? And this has to do with some of the properties of the projection matrix M. You can recognize, by the way, this is M here, all right? That's the projection matrix we saw it before. And if you remember, we said that the projection matrix has k plus 1 eigenvectors x times beta with an eigenvalue 1. So this particular matrix now, I plus c times the projection matrix, is going to have k plus 1 eigenvectors x beta with an eigenvalue that is 1 plus c. So if you think of the eigen expansion of this matrix, then effectively the determinant of that matrix is going to be 1 plus c to the power k plus 1. And there is another little detail that I also had reviewed a little bit earlier when we talked about the projection matrix M. This matrix here is n by n, so the question is where are the other n minus k minus 1 eigenvectors and corresponding eigenvalues of this matrix? And it turns out that the remaining eigenvectors are the vector z in the null space of X transpose, and those vectors z are eigenvectors with eigenvalues equal to 1. And we discussed earlier in the lecture today that there are n minus k minus 1 eigenvectors z from the null space of X transpose. So the total determinant of this matrix is the product of the eigenvalues. So it's 1 plus c to the power k plus 1. That's the multiplicity of this eigenvalue, 1 plus c. And then I have eigenvalues 1 with multiplicity 1 minus k minus 1. And that's how we got that term 1 plus c to the power k plus 1. So I want you to remember, if I can write this equation, this is the result that you see on the bottom of the slide, where for a given c, it gives us the marginal likelihood. All right, so that's the marginal likelihood for a given c. Now, to do calculation of the Bayes factors, you are going to have to apply the hypothesis H0 that beta I is equal to 0. So you're going to have to start dropping one input variable, if you like, or input dimension out of your model and reevaluate the marginal likelihood, and that will allow you, by taking the ratio of the two marginal likelihoods for the model H, for the hypothesis H1 versus the hypothesis H0, and that will give you the Bayes factor. Okay, so let's visit that problem where you start throwing one variable out of the model and then recalculating everything. To do that, let me generalize a little bit, right? So we're going to be interested eventually to drop one random variable out at a time, but let's say that somehow I'm introducing a null hypothesis, H0, where is of the form R times beta equal to R, where R is a matrix Q by K plus 1, and we're assuming that this matrix R has a row rank Q. So basically the Q rows of the matrix R are independent, which effectively means that if I have a constraint like that and beta is of dimension K plus 1, that somehow I can write K components of the vector beta in terms of the remaining K plus 1 minus Q components of beta, and I call all these remaining components of beta as beta 0. So effectively, I can write, based on this, right, I can write Q of the components of beta as linear combinations of this vector beta 0 that involves the remaining k plus 1 minus q components. And that means that I can actually write x times beta in the form of a new matrix x0 times beta 0, where beta 0 is a vector of dimension k plus 1 minus q, and x0 is a design matrix that has dimensions n times k plus 1 minus q. And how do I get this matrix x0? I can write beta either using each component of beta being a linear combination of beta 0, or having each row having many zeros and only one. So for those k plus 1 minus q components that constitute beta 0, these vectors are going to look like 0, 0, 0, and suddenly a 1, and then 0, 0, 0, etc. Okay? So x0 times beta 0 is equal to x beta, okay? And I can write, if I have a constraint of the form r beta equal to r, where r is this q by k plus 1 matrix, I can write my whole regression problem in terms of a new design matrix x0 that you see here, and a new parameter vector beta 0 that is now of reduced dimensionality k plus 1 minus q. Now what I can do is I can write my likelihood model now, because x beta becomes x0 beta 0. I can write my likelihood model like that, right? So instead of having beta and x, I can have now beta 0 and x0 under this constraint. And the only thing, and this is important, I am going to keep the noise the same for both the model where all the parameters are kept, and the model that I am dropping the parameters down to this vector beta 0 and my design matrix to this matrix x0. Okay? So under the hypothesis h0, I'm going to assume that the noise is the same as for my original full model. Now what you can do is, you can introduce now for this new regression model, you can introduce priors for beta 0 and sigma square, and you can use the same structure as what we had before. So this is a Zellner G-Prior. This is the new prior mean for the vector beta 0. And you notice here I use, for scaling parameter c, I use a new parameter sigma c0, okay? Sigma square remains exactly as before, and my design matrix now becomes x0. So in my prior, I'm going to have x0 transpose x0 inverse. Now I can go and cut and paste the formula for the marginal likelihood that I had before in terms of c, x and beta and sigma square, and put now x0 and beta 0, and I can write my marginal likelihood exactly as before. And this is what I have here. All right? It's my new alternative regression model that lives in the space of these parameters beta 0 with design matrix x0 with this constraint. I cut it and pasted the same formula, and the only thing you need to pay attention is that in the determinant of that matrix before that I had, that came out to be c0 plus 1 to k plus 1, now I have k plus 1 minus q, k plus 1 minus q independent columns in the matrix x0, so that determinant will come to be c0 plus 1 to the power k plus 1 minus q, so that is being modified, okay? And here is the Bayes factor. All right, here is the Bayes factor. It's very nice that this Bayes factor is in a closed form. We're using the sigma squared to be the same noise. By the way, if you don't use sigma squared to be the same noise, you're going to have troubles, because the Bayes factor will not be defined. Because you remember, when you compute Bayes factors, improper priors are bound, and the Jeffreys prior 1 over sigma squared is an improper prior. But there is another problem, and this other problem is that I have this parameter c0 and c, and I can make this Bayes factor to be anything I want to by playing with the ratio of c0 over c. So the biggest factor can go from 0 to infinity when this ratio goes from 0 to infinity. So you are going to have to do something to actually eliminate this problem, this dependency on this ratio C0 over C. And that something is this prior that I stated before for beta 0 given x0 and sigma square. Rather than stating it like that, I'm going to have to introduce what's called a consistency relation. I'm going to have to make this prior to actually be a prior that is derived by the generic prior, but projecting beta to the subspace that is defined by my constraint r times beta equal to r. Okay, so somehow you're going to have to consider a consistency condition that tells you that this prior is the projection of your general prior to your constraint. Okay, if you do that, then it turns out that this parameter tilde of B0 and C0 are uniquely defined from your original prior model, and there is no issue such as the one that I mentioned here of the Bayes factor going to any values as you change the ratio C0 over C. So as a matter of fact, C0 comes to be equal to C, and I'm going to show you in the next lecture of what tilde of beta 0 is going to turn out about. But once you have that consistency, you have a Bayes factor, and the table that it was shown to you before uses this equation to evaluate the Bayes factor 1, 0 for each parameter I, where for each I am using the constraint to eliminate the I variable out of my model. So the H0 model would be, let's say, the model where variable 1 is out or variable 2 is out, etc. So I'm repeating this 11 times for my parameters from the Bayes term to beta 1 to beta 10. And so I calculate all the corresponding Bayes factors, and then looking at them, I can decide if there is an evidence for the hypothesis of keeping beta I equal to 0, or for the hypothesis beta I equal to 0 versus keeping beta I in my regression model. Okay, so let me stop now, and we will come back to complete this lecture. So there is an effect that this scale C parameter has in our predictions. So we're going to try to eliminate that dependence in the next lecture. And once we do that, we're going to start trying to do variable model selection, where rather than going through all the possible models, that there are many, where we decide if we're going to keep a variable in or out of the model, we're going to try to address this problem using Monte Carlo sampling, and in particular Gibbs sampling. So that will be a good way to integrate our last few lectures with Gibbs sampling in the context of variable selection in a Bayesian regression problem. Thank you again for listening to this very long lecture. I hope you find the information useful. And again, I try to put enough details so the lecture can stand on its own without having to listen to any of the previous regression lectures. See you in a few days with a continuation of this lecture. Bye.